What if a rocket engine could launch to orbit, land, and fly again, hundreds of times? Elon Musk's SpaceXRaptor engine is rewriting the rules of spaceflight. Join us to explore this game changer. Rocket engines have always been a compromise. They burn violently, waste fuel, and often destroy themselves in the process. They are machines that fight against physics tooth and nail, barely holding together long enough to do their job. For decades, this was just accepted as part of spaceflight. But imagine a rocket engine so radically designed, so meticulously optimized, that it can launch a spacecraft to orbit, return to Earth, and do it again and again without ever needing to be repaired. Imagine that same engine powerful enough to carry a ship fully loaded across the millions of miles from Earth to Mars and then bring it back. That is the SpaceXRaptor engine, a piece of engineering so bold and complex that it once existed only as a theoretical endpoint, a kind of propulsion holy grail. It's the first engine in history to fly using a full-flow staged combustion cycle, a design that squeezes every possible drop of energy from its fuel and oxidizer without letting anything go to waste. For decades, the world's best engineers saw this concept as brilliant but too difficult to build. SpaceX not only built it, they are well on their way toward mass production. Raptor is made for reusability, not retirement. It's designed to take off, land, and launch again with minimal work in between, a complete shift in how we think about access to space. And here's the twist. Raptor is methane-fueled, clean-burning, designed with Mars in mind, and tightly aligned with the goal of building a multiplanetary civilization. Stick with us, and you'll soon see why the Raptor engine doesn't just break records, it breaks the whole spaceflight industry. No revolution begins fully formed. The Raptor engine, with all its radical innovations and record-shattering numbers, started its life as something much more humble, a question. Could there be a better way to build a rocket engine? Not just marginally better, but fundamentally different? That question began taking shape around 2009, when SpaceX started sketching out a high-performance engine concept built around a staged combustion cycle. In traditional rocket engine designs, some fuel is burned not to produce thrust, but just to drive the pumps that push the rest of the propellants into the combustion chamber. That turbine exhaust is then discarded, still loaded with unused energy. It's a little like lighting part of your gas tank on fire just to power your car's engine fan. The Raptor doesn't do that. It uses what's known as a full-flow staged combustion cycle, a propulsion concept so advanced that, until Raptor, it had never flown. In this architecture, both the fuel and the oxidizer are completely gasified in separate pre-burners. These superheated gases are then sent through turbines that drive the engine's pumps. Instead of being vented away, the gases are routed into the main combustion chamber, where they ignite in a final high-pressure burn. Every molecule of propellant contributes to thrust. There's no waste, no dump valves, no fuel-rich smoke trailing away from the rocket. That closed-loop design makes Raptor far more efficient than open-cycle engines. It also spreads the thermal load more evenly, reducing the stress on individual RTO. The turbine exhaust runs cooler, which extends the engine's operational life, a crucial requirement for missions where repairs aren't an option, like landing on the moon or returning from Mars. But none of this came easy. Full-flow staged combustion is a beautiful idea on paper, but it's notoriously hard to build. When methane and oxygen are pre-burned at different ratios and then recombined, the system becomes incredibly sensitive to timing. Even a slight mismatch in ignition can cause combustion instability, violent oscillations that ripple through the engine like a hammer. Left unchecked, they can shatter components in milliseconds. To make Raptor viable, SpaceX had to fine-tune the ignition sequences inside the pre-burners, adjusting how and when fuel was injected to smooth out the flame and stabilize the flow. With a design like this, fuel choice becomes critical to the engine's success. At the time they began designing the first Raptor prototype, SpaceX was looking at hydrogen as the fuel of choice, which made sense. Hydrogen is the lightest molecule in the universe, and when paired with oxygen, it produces some of the highest efficiency engines ever flown, like the RS-25 on the Space Shuttle orbiter. But hydrogen comes with baggage. It's hard to store, prone to leakage, and demands cryogenic conditions so extreme that entire rocket designs have to bend around it. For a company focused on reusability and simplicity, that didn't sit well. By 2012, the focus shifted. Methane entered the picture, not just because it was easier, but because it made more sense. One of the biggest challenges in space exploration is that rockets have to carry all their fuel with them. That's fine for short trips to orbit, but when the destination is Mars, carrying a full round-trip fuel supply quickly becomes impractical. Methane solves this problem. The Martian atmosphere is made up almost entirely of carbon dioxide. Using a process called the Sabatier reaction, carbon dioxide can be combined with hydrogen to produce methane and water. The water can then be split into oxygen and hydrogen, creating a full fuel and oxidizer supply from local resources. This means a Starship could land on Mars, produce its own fuel, and launch back home without ever needing a resupply chain from Earth. 3 years after development began, SpaceX was ready to bring Raptor out of theory and into the real world. In 2016, at their test facility in McGregor, Texas, they fired the first full-scale Raptor engine. It marked a historic moment, the first time a full-flow staged combustion cycle methane engine had ever been ignited. That test didn't make news headlines, but inside the aerospace community, it sent a ripple. Full-flow staged combustion had been attempted before in the Soviet RD-270 and the U.S. Integrated Powerhead Demonstrator, but neither of those engines made it off the ground. From the moment it left the test stand in 2016, Raptor has been in a state of constant transformation, driven by SpaceX's philosophy of rapid iteration. Each new version hasn't just improved performance. It has reshaped the engine itself, cutting weight, increasing efficiency, and making production faster and cheaper. Raptor wasn't designed in isolation. It was built for a specific mission, one that requires an engine capable of more than just lifting payloads into orbit. It needed to be powerful enough to launch the largest rocket ever built, efficient enough to operate in deep space, and durable enough to land and fly again, over and over. That vehicle is Starship, and together with its super heavy booster, it forms the foundation of SpaceX's plan to make space travel routine and interplanetary colonization possible. At the base of SpaceX's fully reusable launch system is Super Heavy, the first stage booster that will loft Starship out of Earth's atmosphere. Unlike traditional boosters that drop away and burn up, Super Heavy is designed to return to Earth, land vertically, and be used again. But doing that at such a massive scale requires an engine with extreme power and precise controllability. Super Heavy is fitted with 33 Raptor engines, producing an unparalleled level of thrust. At full throttle, the combined force of these engines generates over 7,800 metric tons of thrust, making it the most powerful rocket booster ever built. It surpasses the Saturn V, which carried Apollo astronauts to the moon, and even dwarfs NASA's modern moon rocket, the Space Launch System, in raw power. That thrust isn't just about brute force. Super Heavy must also perform controlled landings, meaning Raptor's ability to throttle down to 40% power and restart reliably is just as critical as its top-end performance. Unlike engines that are used once and discarded, Raptor is built to return, refuel, and launch again with minimal downtime. Perched atop the Super Heavy booster is Starship, a vehicle designed to go far beyond low Earth orbit. While Super Heavy gets it off the ground, Starship is built to carry people and cargo to the moon, Mars, and beyond. To pull that off, it needs engines that can handle two very different environments. For takeoff and landing, Super Heavy uses sea-level Raptors, tuned to work in the dense air near a planet's surface. But once the Starship upper stage is out in the vacuum of space, it will also utilize vacuum-optimized Raptors, or RVACs, with extra-wide nozzles specially designed to get the most out of every drop of fuel in zero atmosphere. Starship carries a total of 6 Raptors, 3 of the standard sea-level engines for steering and landing, plus 3 RVAC engines for maximum efficiency in the vacuum of space. That efficiency is crucial for long-duration missions, where every bit of fuel must be used as effectively as possible. It means Starship can carry heavier payloads, travel longer distances, and operate with greater flexibility in deep space. The original Raptor, later coined Raptor 1, was an engine of firsts. It was the first full-flow staged combustion cycle engine to ever fly, and it was designed from the ground up to run on methane. Even in its early form, it was more powerful than most operational rocket engines, producing 185 metric tons of thrust with a chamber pressure of 250 bar. That pressure was already higher than anything in service at the time, but it wasn't perfect. At 2,080 kilograms, Raptor 1 was heavy, giving it a thrust-to-weight ratio of 89.1, respectable but not ideal for a fully reusable launch system. It was also complex, filled with flanges, welds, wires, hoses, and bolted joints that made manufacturing slow and expensive. SpaceX had proven the technology worked, but it wasn't yet something they could build at scale. In 2021, SpaceX rolled out Raptor 2, a drastic departure from its predecessor. It wasn't just an improvement, it was a complete rethinking of how Raptor should be built. Every part of the engine was redesigned to be simpler, lighter, and more powerful. The first thing to change was thrust. Raptor 2 produced 230 metric tons, a 24% increase over Raptor 1. Chamber pressure jumped to 300 bar, pushing the engine even further into record-breaking territory. At the same time, weight dropped dramatically. Raptor 2 came in at just 1,630 kg, shaving off 450 kilos from the original design. That weight saving alone made it one of the most powerful engines ever built relative to its mass. And then there was the cost. SpaceX has always focused on reducing manufacturing expenses, but Raptor 2 marked a turning point. By simplifying the design, eliminating many bolted joints, reducing welds, and integrating components into larger single pieces, they slashed production costs by 50% compared to Raptor 1. For an engine that was going to power Starship, which uses up to 39 Raptors per launch, this wasn't just an improvement, it was the only way to make SpaceX's long-term vision financially viable. By 2024, SpaceX had taken everything they learned from Raptor 2 and pushed it even further with a new prototype engine, Raptor 3. Thrust climbed once again, reaching 280 metric tons, a 22% increase over Raptor 2. Chamber pressure soared to 350 bar, shattering all previous records. No other operational rocket engine has ever reached such high pressure. Weight continued to drop. Raptor 3 came in at just 1,525 kilograms, bringing its thrust-to-weight ratio far ahead of competitors like the Blue Origin BE-4 or the long-standing Russian workhorse, the RD-180, and making it one of the most efficient engines ever built. One of the most groundbreaking improvements was in cooling and durability. Early Raptor versions required external heat shielding to protect the engine's plumbing and components. Raptor 3 integrated cooling channels directly into the structure, eliminating the need for extra shielding while also reducing mass and complexity. The result was a leaner, tougher, and more powerful engine, one that could be produced faster, cheaper, and at a scale never before seen in rocketry. And if history is any guide, Raptor 3 won't be the last iteration. With each new version, SpaceX has made the engine lighter, stronger, and easier to build, and they're not done yet. The company is already working on an even cheaper and more powerful design, setting the stage for an era where Starship launches are as routine as commercial flights.